Before starting this video, I want to let you guys know that Coding Cleverly also has a Patreon page. So go to patreon.com/codingcleverly and you'll see that there is a Patreon page that is available, and you guys could support the channel by just joining any one of these tiers. You guys also could become my patrons. That would also motivate me to provide better and better content. So all you got to do is go to this page and show some love to Coding Cleverly. Enough with the shameless plug. Now let's go to the video. What's poppin', guys? This is Coding Cleverly, and today we're going to be talking about the heap data structure. As usual, I'm not going to start writing the code out first. First, I'm going to talk about what heap is, and then after that, we're going to talk about the different types of heaps, and then we're going to start explaining it, and then finally, we're going to go and write some code and then execute it. We created the tree data structure in the previous video, and then we also created a binary search tree, also known as a binary tree. So similar to those videos, we're also going to use the variant of a tree data structure, but in this case we're using a heap. And heap is a data structure that is a specialized form of a tree data structure, and it actually satisfies the heap condition. Heap has two different types. One is called the max heap and the other is called the min heap. In a max heap, for every given element, now every given element here is talking about every single node in that tree except for that root node. So in a max heap, for every given element, its parent's value is greater than or equal to its own value. So we always have the parent that is greater and equal to its own value, the child's value. But in case of a min heap, we have something reverse. So for every given element, its parent's value is less than or equal to its value. Now, heaps are described as binary trees because each parent node in a heap has at most two child nodes. It looks pretty much similar to a binary tree. So heaps are described as binary trees because each parent node in a heap has at most two child nodes. It can't have more than two nodes. Although this is the case, heaps are most commonly represented with an array list in Java, since this data structure is much easier to implement than a full tree class. We're going to use the array list data structure that is already built in for us in Java to create our heap. Min heaps efficiently keep track of the minimum value in a data set, even as we add and remove elements. On the other hand, if you talk about max heaps, they keep track of the maximum value in the data set. We will keep track of integer values in our heap, and we will store this minimum value at the root or top of the heap. So in this case, if you look over here, this top portion, which is right here, this is called the root. And this is also having the lowest or the smallest value in the entire data structure. In a min heap, we're going to store the minimum value at the root or top of the heap. So if we look at this structure here, we have to guess what this is. First, we could see that the root is 5. We can automatically deduct from here that this is a min heap because the minimum value is on the top. So heaps have many applications, but the most common ones that you'll see are that they're used to solve complex problems such as finding the shortest path. You could say Dijkstra's algorithm, or efficiently sorting a data set. That's called heap sort. Heaps are an essential tool for confidently navigating some of the difficult questions asked in a technical interview. Heaps are always added like this, from left to right. So if you want to add a new element, it will be from here. Then after that, it will be from here, then added here, then here, and then it will just go here and here. First of all, we're going to create the array list. So I'm going to say public, and we're going to say public array list. And we're going to put the integer type here. And the name of the variable will be called heap. And here we want a size to. We'll say public int size. After that, we want a constructor. So we can say public min heap. No input parameters. This is going to be the default constructor. It will create the heap, so this dot heap, and it would equal to new array list. The type is integer, and the other case here we want is the heap just have something null for now, and I'll tell you why. So we're adding one thing for the heap, and that is, so we're using this dot heap dot add method available in the array list, and we're adding null. This is going to be in its first index, and then after this dot size 0. Okay, so because we have red underlines here, we have to quick fix and we got to import the array list. This is going to import it on the top, import java.util.arraylist. We have no problems here. Head cannot be resolved, or it's not. Actually, it's heap. Let me explain why I added null here. because I'm not going to start with the 0th index, we're going to go always with the 1 index here. We're not going to start with the 0th index at all. So we're going to create an array list. So in case of a heap structure, we're always going to have the 0th index occupied by null, and we're always going to start with the 1 index and then 2. So 2, 3, 4, all the way to the last one. The last one now will be easily accessible as the size. So whatever the size will be the last one. So we're always going to have the size as the last one. In case last time we used to do size -1, so now this time we're going to use size as the last element in our array list. Void add, and here we're going to create a value that we want to pass in. So this dot heap, and we're going to have a dot add. We're going to put in the value. There you go. Perfect. Because it's dynamic and we could add as much size as we want, we'll just have the size incremented here, the variable. This dot size plus equal to 1, adding, and then we have the plus, so value here, and then the semicolon at the end. Okay, cool. Now we have that done. We also want to print out the heap, so we could print it out using system.out.ln, and we could just print it out using this dot heap. Cool. Now normally whenever we call the add function, we're gonna have to add something from the left side, and then we could go all the way to the right. But let's say we have some value and I said I put in 3. Now this actually destroys the heap condition. We have to satisfy the heap condition, and we gotta move our way up so we could readjust things and place this 3 all the way to the top. So we have to like do some kind of process, and that process is gonna be called bubbleUp. And what we could do here is that we'll check the parent. We could see if the parent is greater or less than. So if the parent is greater than our child, then definitely we need to swap elements. So this 25 will now have the 3 over here, and this 3 will be now called as 25. So once this is happening, we're gonna actually go and bubble up again and see if that parent is 10 now. That is also bigger, so we're gonna have 3 over here, and this portion will have 10. So this has had a swap again, 2 times swap, and then the last time we go over here and see, oh man, the parent's still bigger, so we're gonna swap again. So 3 over here, and then we had 5 over here. So in total we used the swap method 3 different times, and we finally got our value up on the top. Now the heap is fully satisfied, the heap condition works. The smallest value is on the top. The children are always greater than the child, so you can see over here 5, and the children are greater, and that's perfect. The method that we have to apply here is called the bubbleUp. So I'll say this dot bubbleUp, and this is a method that I'm going to have to create. So I'm going to say bubbleUp. So I'm going to define it somewhere on the bottom. I'm going to create this as private because we're only allowed to access this within the class. Void bubbleUp. And here we're gonna say int current this dot size. We could get the index of the last element by using this dot size, and this would give us the current element. So in this case it would be the element that was over here. I guess it was 3. We have to check if the current is greater than 1, meaning if the current is you know, the index is greater than 1. If it was equal to 1, it was not gonna have any parent. So we should have a parent here. This dot heap dot get, but we actually need the parent index, and we also need the child index. So for this case, we need the index of the parent, the index of the right child, and then the index of the left child. We created some helper methods that would help us to solve this problem. To get the parent index, we get the current. So current is always going to be our thing that we added. So if we want to get the parent, we could divide the index by 2, and we get the floor division. So if I say the current was 9 divided by 2, I get a 4.5. I get a math.floor. That means that's going to be 4, and it's going to be an int 4. So that's the index, and that's going to be my parent, 100%. If I want to get the left child, I get the current passed in. I multiply that current with 2. Let's say current index was 2. If I multiply it with 2 now, it's going to be 4. So the 4th index will have my left child. The 5th index will have my right child if I multiply it with 2 and plus 1. So these are my helper methods, and I'm going to use those helper methods to create that condition that I'm using in this bubbleUp. So to get the parent of this, I could use this dot getParent. This is the method over here, and I'm just going to pass in the current. Have that greater than. If that is greater than, then we have this dot heap dot get, and then we have greater than this dot heap dot current. First of all, if it's greater than 1, the index is greater than 1, and if this dot heap dot get parent's value, so this dot parent will get the index, and this get method will return the value of the parent. So just think of this whole thing as the parent value. If that's greater than now this .heap.get current, this is the current value. If the parent value is greater than the current value, so we could say system.out.println, and here I'm gonna say swap index, and I'm gonna have the current index swapping with of the parent. So for that we could have plus, and we could say this dot get parent, and to get that index we just pass in the current. Awesome. So this is just my print statement. It will tell everyone what I'm doing here. After this, we're gonna print out the current heap to show what the content looks like. The heap is actually the array list. So whenever I call the heap, alternatively I mean the array list. So system.out.println, and I'm calling the heap here, so the array list, and I just call it this dot heap. And this is gonna print out the contents here. Then after that, we want to swap it. So we could use the swap method, and we're gonna also define this. We're gonna pass in the current index, and we're also gonna pass in the parent index. So we this dot get parent index, and we're gonna pass in the current like that, semicolon at the end. So right before my helper methods, I could add in my swap method. So this is the conventional swap method, and we have two integers. We created a temp, and we said this.heap.get. So b, this gets the value of b, and we put that in the temporary. So the b will be, in this case, it would be the parent's value. And we have this.heap.set. Now we want to assign the b's value, the parent's value, with this.heap.get the a value, which is the current value. So the current value will be now assigned to the parent value, and then after that, this.heap.set of the current value, the original current value, will now contain the temp value, which was back in the b value, which is the parent value. So it's just like a swap. Perfect, we're done with that. So the last condition, the last statement to add, so that the while loop could just work on until we have our heap fully satisfied, is that we have to add this final statement. This final statement is gonna assign the current now, because the current will change, and we'll say this.getParent. So the parent will now be assigned. So whatever the current index was now will be assigned to that current variable. Awesome. So that this will make our repetition, and it's just gonna go up, and the bubbleUp process will work 100% correctly. Once we are done with this, we could easily add stuff to our heap. Now we're gonna create the pop method. So I want to ultimately remove this top thing over here, but if I try to remove it like this, I'm gonna leave these two as orphan nodes. I don't want to do that. That's just gonna ruin my entire heap structure. So I'm gonna have to provide some kind of mechanism here. We have the minimum value here, and we have the last value, which is on the right side of the min heap. So we could replace these. We could swap them, because this doesn't have any children. So the heap condition wouldn't break or anything because it doesn't have any children. So we could swap this 18 with this thing over here. So we could have 18 over here, and we could have the 5 here. So 5 will be over here. Now we could easily remove this thing. So we could say remove, use the remove method. So that's gonna be our popMin method. Now we have to apply the heapify method here, because this tree is not showing a heap anymore. So what we're gonna do is we're gonna try to provide heapify, so that 18, which is over here, is definitely not gonna be here. It's gonna go downwards. And you can see over here we have 10 and 10. So we'll have to look at the smaller value. But in this case, both are the same, but we're gonna choose the left side. So we're gonna swap it with this one. We're gonna say 18 will be over here, and 10 will be up here on the top. After that, we have the left and right over here, and we look at the smaller value. So we put 10 on the top, so we swap with 10, and then we have the 18 on the bottom. So once we completed this heapify process, we finally end up with proper heap conditioned tree, which has the root node, which is less than or equal to its children, and then the parents over here are less than or equal. So in this case, they're totally less, and these children are much greater than the parent. So this is what we had to end up with. This thing is not part of the thing anymore because you removed it. So as opposed to the add method, which we used a bubbleUp, which goes from the bottom to the top, we're gonna use the heapify process that goes from the top to the bottom. So the direction is reversed. And let's get started with the code. popMin, no input parameters, and we're gonna first check if the size is 0. If it is, we're gonna throw out that the heap is empty. So we're gonna say if this dot size is equal to 0, we're going to throw out an error. We're going to say throw new error. We'll say heap is empty, and we'll put a semicolon at the end. Now we're going to put a system.out.println. So this is the thing that we're going to be applying. So I wrote a string here, system.out.println, swap min element, this.heap.get. Index 1 always has the min element. Remember, index 0 has null. This is our structure here. Null is this one, just made it simplified. So 1 has the first element in the heap. So one element, one index is always the root. And last element, this.heap.get, this.size. So I told you that this.size will have the last element. So we swapped the two. Right now we didn't. We just print the statement. We're going to swap them here. This process, first we're going to swap it using this.swap 1 with this.size. So this is swapped. After that we have int min. Remember, like I said, when we swap it, the condition will be still broken. The heap condition is broken. So we need to produce some kind of heapify process. But before that, we're going to get the min value. So this.heap.remove, and we're going to say this.size. So the last element will be removed from our structure. System.out.println removed from the heap min. System.out.println this.heap will just show the heap structure again with the removed value. After the removed value, it will show how the heap looks like. It will decrement the size, and then after that we'll use the heapify process. And once we're done with that, we'll return the min value which we removed from here. So after this popmin, we're gonna add in the heapify method. I'm just gonna paste it here. And also before that, I'm gonna have to add this. So I'm just gonna readjust this. So this popmin will be up here. So after the add method, we're gonna have the popmin method. So we're gonna have the add method and then the popmin method. Because the add method is calling the bubbleUp, so the bubbleUp should be right here. And because the popmin is calling the heapify method should be right here. This is how the layout should be. And now let's discuss what the heapify method has done. So the same explanation that I did in the diagram is now mapped out in code. So the first thing is that we got the current, and that is the first index, the root node. We got the left child with the getLeft current index and getLeft. So these helper methods are available, and we just got the left and the right child. We provide a while loop, and we say this.canSwap. We want the current left child and right child. We provide this kind of condition because we want to know if the left child and right child are available, and we also want to know if the left child and right child have greater values than compared to the current value. To do this, we're going to have the canSwap method. So this is where the canSwap method will be. It would also need the exist method, so I'm going to have the helper method exist over here as well. There you go. So now let's discuss these helper methods first, and then after that we'll go over here. Exist method will just get the index of the array list. After that it would say return index less than equal to this.size. If the index is less than the size of the array list, we could say yes, it exists. So the exists meaning, like, we have the index, let's say it's the root node, and it's always 1. It's always going to be less than or equal to its size, right? It's always 100% this is going to be possible. So if this returns true, we have something that exists. The canSwap method implies that we have the current index, the left child index, the right child index, and we say return this.exists. If the left child exists and first we're going to check the left child, because by default in binary trees or heaps, we're always going to be working with the left child first, and then we're going to look at the priority of the right child. If the right child for some reason doesn't exist, we're always going to look at the left child, and we're going to use that. Heaps and binary trees will always have the left child and then the right child. You'll never have some kind of implementation where there's just going to be a right child and no left child. That's not possible. So over here we have this.exist left child and this.heap.get current. So we're getting the current root. So we're getting the value for that. And I'm saying if that value is greater than this.heap.get left child. So we're saying if the value of the root is greater than the value of the left child, and we're going to have to swap this then. Or the other condition is that if the right child exists, in this case that the left child is also existing, and this.heap.get current, the current value is greater than the heap's right child. So we're also going to switch here. So we never want to have our parent have something greater than our children. So that's the condition for min heap. This.canSwap current left child right child. So the condition is like if the current child exists, the left child exists, and the right child exists, and if the current value has greater than the left child and right child. So if this.exists left child and this.exists right child. So now in two cases, if both of them exist, what we're going to do is that we're going to say if this.heap.getLeftChild is less than this.heap.getRightChild. Now this means, I'm going to tell in simple words, this means the left child value is less than the right child value. So you have the right child value greater. Now we're always going to prefer the smaller value. Why? We're using a min heap where we're trying to get the minimum value. Because we're over here, the current is over here, and we're looking at the left and the right child. We're always going to prefer something that's smaller, not 13, but we're always going to look at 10. Because we're using a min heap, we want the smallest value on the top. So that's why we're going to swap with the 10 value. And this 10 value should be 10 over here. The parent should be over here. So that's the thing. That's what I'm trying to apply here. If the left child has lesser value than the right child, that's what I said in the diagram. We say this.swap with the current and the left child. We assign the current to the left child index. Else we say this.swap, because if the right child is smaller, we say current swap with right child and current is equal to right child. Now the other condition is that if we don't have the left child and the right child existing, but we only have the left child existing, so we say this.swap with the current and left child, and we assign it with the left child. Over here, this line and this line. So we have the left child and the right child. So we want to adjust its variables as well, like how we did for the current, because the current now has some either left child or the right child. So the left child will now be the getLeft of the new current. So the new current is left child, so we're going to get the left child of this thing. And for the right child, we're going to get the right current. So the current this.right getRight, and we're going to get the current. So because we reassigned the current variable, we also need to reassign our left child and right child variables. And since we have the current now set to left child or set to right child, we want the left and right childs of the new current variable, which is over here. To do this, we could say this.getLeft of the new current variable, and we assign that to the left child, and then this.getRight of the new current variable to get the right child. In the main method, we have public static void main string args, command line of arguments, until here. We created an instance of the min heap class and call it min heap. We got a random r, now new random, and this is going to create random numbers. Now you can see over here there's a for loop that goes from 0 to 6. That means it works 6 times. We're gonna get a random number here from r.nextInt, and we use bound 40. Now this means we're gonna get a random number from the range of 0 to 39 always. So this is gonna apply like that. And after that, once we get our random number, we add it to our min heap using minheap.add int underscore random. After that, when we have 6 random numbers inside of our heap. And also the other thing here is that when we use add, we're actually calling the method here. So add is also calling bubbleUp. So first it's printing adding value, and it's also bubbling it up. So it's bubbling up to satisfy the min heap property as well. To bubble up is this one. We get the size, the current, the last element, and we also perform this swap index. We're swapping and readjusting to get the bubble up process. Here we're also gonna, once we're done with that, you're gonna see this printing out like 6 times or something. And then after that, we have remove minimum value multiple times. So we're gonna remove the values from 0 to 6, and we're gonna say popMin. So it's just always gonna remove the root node, and then it's gonna readjust its pointer. So if you go to the popMin method, it's gonna, first of all, it's gonna say swap the element. So we're swapping it, and then after that, we're gonna remove the value because we're swapping it because we wanna first get the greater value and then swap it to get it in the right side and remove it easily from there. And then after that, once we've removed it, we decrement the size. We use heapify to satisfy our heap condition. So this heapify method will be called, and whatever's inside the swapping mechanisms will all be happening. And then once it's done, we can say heapified and minheap.heap. We just print out the heap once it's heapified. So every time, like 6 times, it will be printed out for heaps. So let's compile it up. We're gonna use javac minheap.java, and to run this, we're gonna say, we're gonna remove that. And there you go. We got, first of all, we added 9. So these are random numbers removed from the heap. 1, 2, 3, 4, 5, and then we have 6. And at the end, we end up with an empty min heap with the first index set to null, because we explicitly said that having null in the 0th index means that it's completely empty. So in min heaps, we discovered that the parent values always have values less than or equal to their child values, meaning that the child values will always have greater values or equal values to their parent values, but the parent values will always have something less. But in case of max heaps, which I want you to implement, you want to have the parent value greater than or equal to its own child values. So we'd have parent value, let's say 25. So we'll just put a 25 over here. So 25 is greater than and equal to its parent value. So you want to create something like that. Try to this implementation on your own. This will be an awesome learning experience for you guys. So if you want to support the channel, you could become an official patron by going to patreon.com/codingcleverly and selecting one of those tiers. That's it with this video, and peace out.